morning. So today what I'd like to do is to finish up our discussion of Chapter 7, and specifically to go into some of the details of how reactions occur, how substitution reactions occur, and to get a better feeling for the properties of the electrophiles, the leaving groups, and nucleophiles in these reactions. One of the things we're starting to learn is that there are many different modes of reactivity, and often there are subtle differences in reactants that can lead to a reaction in one way, a reaction in another way. We've seen, for example, reactions through an SN1 pathway where we get a carbocation, stereochemistry in the center that's reacting is lost. We've seen reactions through an SN2 pathway where we go through no intermediate, where the nucleophile comes in, the leaving group leaves, and we never get a carbocation, and stereochemistry is inverted. And as I said, we've hinted a number of times in the next chapter, we'll be seeing elimination reactions of the same alkyl halide. So I'd like to start by making a little bit of sense of one thing I've been talking about, and that's the difference in when SN1 and when SN2 reactions occur, and then we'll go into the why. One thing I like to do is to keep in mind that first and foremost, in thinking about SN1 and SN2 reactions, the same logic is going to apply to E1 and E2 reactions, is the nature of the alkyl halide. So if I'm going to make a little table here where we're comparing SN1 and SN2 reactions for various alkyl halides, if our alkyl halide is a tertiary alkyl halide, then we would very often see an SN1 reaction for it, but virtually never, I'll say rarely, because I can give you examples that are intramolecular. Very rarely, for your purposes, you could say never, would you see an SN2 reaction occurring. For an alkyl halide that's secondary, sometimes you'll see SN1, sometimes you'll see SN2. They're less reactive in both such reactions. In other words, often secondary alkyl halides will require more vigorous conditions to react at all by any pathway. More heat, stronger nucleophiles, all of these would contribute to reactions. So if I wanted to generalize, I'll write sometimes under both SN1 and SN2. Primary alkyl halides very rarely react through SN1 pathways. Simple primary alkyl halides don't, except under very extreme conditions, but one can apply enough stabilizing groups in some particular cases to get primary alkyl halides reacting to an SN1 pathway. For your purposes, you might want to think never if you're looking for a rule, but as I said, often things are more complicated. But very often, we will see primary alkyl halides react through an SN2 type of pathway. And for all intents and purposes, methyl halides, this of course would be tertiary RX, primary, secondary RX, primary RX, methyl halides, methyl iodide, methyl bromide, and methyl chloride, would never, under any conditions that you could conceive of, react through an SN1 pathway. But on the other hand, it's very common. They're very good electrophiles. They react under mild conditions through SN2 type of pathways. Now, I've been alluding to the reason for the difference for quite a number of times here as we've discussed this, I think all the way back to our discussions in Chapter 6. And this has to do with carbocation stability. SN1 reaction goes through a carbocation that doesn't have a complete octet. The carbocations don't want to form in general, but particularly don't want to form when they are very unstable. And so if we wanted to just sort of generalize, we'd say a tertiary carbocation is going to be more stable than a secondary carbocation, is more stable than a primary carbocation, and that's more stable than a methyl carbocation. And so just to make it clear with structures, a carbocation of this generic structure, not necessarily tert-butyl, but any sort of carbocation that's tertiary, I would say you might see very commonly as a reactive intermediate in a reaction, whether it's an SN1 reaction or an E1 reaction. It shouldn't surprise you that a tertiary carbocation forms. Secondary carbocation, I'll say, forms sometimes, depending on conditions. Primary carbocation, and again, I'm really meaning this as a generic carbocation. I'll write it as an ethyl one. I'll say almost never. And for methyl carbocation, for your intents and purposes, we'll say never. The big difference, big factors that are stabilizing our carbocations are hyperconjugation. I've alluded to hyperconjugation before. The vacant p orbital of a carbocation is so unstable, is so unhappy not having electrons in it, that it wants to get electrons by any way that it can. And one way that it can do so is by borrowing electrons from an adjacent carbon. Let me show you what I mean. So here's a methyl carbocation, CH3+. There's no adjacent atoms, they're just hydrogen atoms. And here's your vacant p orbital. Remember, this representation with the wedge and the hash means that the plane in which the hydrogens lie is the plane orthogonal to the blackboard. The wedged hydrogen is coming out of the blackboard. The hashed hydrogen is going back into the blackboard. And there's a vacant p orbital here. And there's nothing that the molecule, nothing that the methyl carbocation can do to put any sort of electron density into this vacant p orbital. As a result, it's very unstable. And if you were making an energy diagram, you'd think of it as very high energy. Now, by way of contrast, let's take a tertiary butyl carbocation, CH3, 3C+. So our tertiary butyl carbocation also has a carbon with a vacant p orbital. But now, hanging off that carbon are three methyl groups. One of them's pointing out, one of them's pointing back, and we have a third in the plane. And I'm only going to, because there's so many atoms in this molecule, I won't try to represent all of the methyl groups, but what I'm about to show you applies to all three of them. Each of the methyl groups, of course, has a carbon, and that carbon has hydrogens attached. So for this methyl group, I'll represent the hydrogens like so. So now you have a filled orbital, an orbital created by the overlap of the carbon's sp3 orbital with the hydrogen's 1s orbital. And that orbital has electrons in it. And the carbocation looks at this and it says, oh, wait a second, I'm unhappy, I've got a vacant orbital here. And so I can borrow some electron density from this. Now, there's no real good way to show this, but the best way I can represent this is by writing a resonance structure that you wouldn't normally write. I'll call it a non-bond resonance structure. Normally in resonance structures, we move bonds around, but we keep the basic structure of the molecule. What I'm going to do is I'm going to give up the bond here. Remember, we're only mixing in a teeny tiny amount of this resonance structure. And of course, it's not this one hydrogen, because we're also going to mix it in and use a little bit of electron density from a CH bond here, a little bit from a CH bond here. So you could write many such resonance structures. And now, since we've pushed our electron density between the carbons, we can think of us as having a bond over here. And I'll draw in my methyl groups. And I'll draw in my other two hydrogens. And I'm not going to change the geometry of the molecule because remember, resonance structures don't change the geometry of the molecule. So I'm going to draw it just in this way. Just to help you think about it, I'll make sure you know there's a positive charge here. And again, to remind us, I'll make sure you know there's a positive charge here. So this non-bond resonance structure write it as res structure, STR, just as an abbreviation. This non-bond resonance structure helps us see how that extra carbon atom can help contribute electron density from the CH bond. And this one, as I said, contributes a little bit, and this one. In a way, remember I mentioned that resonance structures and molecular orbitals are complementary approaches to thinking about molecular structure. In a way, a molecular orbital approach is better for understanding hyperconjugation, but the problem is you can't really draw a simple picture. This is a very nice simple picture that with a simple snapshot helps show us the way in which the stabilization occurs. What's interesting is under circumstances where you could form a more stable carbocation at this position, you can actually have the hydrogen migrate over in what's called a 1,2 hydride shift, in which this carbon wants the electron density so much it steals not only the pair of electrons, but ultimately the bond to the hydrogen atom. And that's common if you have, for example, a secondary carbocation here and a tertiary carbon here. Right now we have a primary carbon here. But imagine if we had one methyl group on this carbon, two methyl groups on these carbons. Then what would happen is this guy would look and say, oh wait, I'm a secondary carbocation. I'm really unhappy. If I stole that hydrogen with its pair of electrons, he'd be stuck with the vacant p orbital, but he wouldn't be as unhappy. That's called a 1,2 hydride shift, and even that can occur in carbocations because they are so unstable and so prone to trying to find more stable configurations. All of these carbocations, all the ones that form, exist only for a fleeting instant. They're just reactive intermediates that form for a millisecond or a microsecond in the course of a reaction before they react with a nucleophile. So just to sum up this part of the discussion and to bring us back to some of the types of structures that we were talking about at the very beginning when we were discussing SN2 and SN1 reactions, an alkyl halide like ethyl bromide, bromoethane to be more specific, would participate in SN2 reactions. participate in an SN1 reaction. The primary carbocation is relatively unstable. I'll say very unstable, so no SN1. And what makes it particularly good at SN2 reactions is it's not sterically hindered. As we saw in the animation showing the formation of the transition state for an SN2 reaction, that nucleophile has to get in there for that one moment, that one transition state, that 1 femtosecond where the nucleophile is forming a bond and concurrently the leaving group is leaving, and that's really crowded. Primary alkyl halide is the best possible situation with the exception of a methyl halide for avoiding steric hindrance. And then just again for this comparison at the end, I'll say a tertiary alkyl halide like tert-butyl bromide participates in SN2, in SN1, but not in SN2. Too sterically hindered for a nucleophile to get in close. But it participates in SN1 because it can form a tertiary carbocation, which is going to be the least bad sort of carbocation that you can form. Thoughts or questions at this point? Well, let's go on then to talk a little bit more about properties of leaving groups, because you're going to see more leaving groups and more varied leaving groups as you move into the 51B part of the course and begin to learn about alcohols and ethers. So the main thing in leaving groups is that it must be able to accept an electron pair. Whether an SN2 reaction or an SN1 reaction, a leaving group is leaving with an electron pair, and so it must be happy to take that electron pair. What that means is that if your leaving group is a strong base, it's not going to be very good. It's going to be bad. Why? A strong base doesn't want to have that electron pair, doesn't want to have that negative charge. It would rather share it with a proton. What's a bond to a proton? It's a covalent bond. The leaving group would rather be bound to a carbon than leave with its electron pair, just as it would rather be bound to a proton. Now, conversely, if your leaving group is happy to accept an electron pair, then it's going to be a better leaving group. Or in short, the weaker the base, the better the leaving group. Now, thus far in talking about alkyl halides, we've really been talking about iodides, bromides, and chlorides. And I've already said fluoride isn't a good leaving group. It's sort of in a category of its own. That makes sense because fluoride anion is much more basic than, say, iodide anion or chloride anion. So if we look at some good electrophiles, say some good electrophiles here. I'll make a little table. I'm just going to borrow from examples that we've already used, and also I'll use this as a chance to remind us of their anatomy. So in the course of our discussion in Chapter 6 and Chapter 7, we've seen ethyl iodide as one electrophile, CH3, CH2I. And I just want to go through and take a moment to really think about the anatomy here. So when we've seen ethyl iodide react as an electrophile, our leaving group is an I-. It's the iodide anion. Now, how do we know if that's a strong base or not a strong base? We consider its conjugate acid. The conjugate acid of iodide anion is HI. It's hydrogen iodide. Now, this is the reason why I said there's certain pKa's that you should have a good feel of. Remember when we started talking about acids, and I said some of them just you should have a good idea of. And so let's use some of that knowledge. We said that HI was a strong acid. Its pKa was approximately -10. It's so strong, it's really hard to measure exactly because if you put hydrogen iodide into water, it completely dissociates to H3O+. We looked at bromotriphenylmethane in SN1 reactions. In fact, we even had it on the previous quiz in a degenerate SN1 reaction where we talked about energy diagrams. And the leaving group in this case was bromine, Br-. The conjugate acid was HBr, and the pKa of HBr is about -9. In other words, HBr is a very strong acid. Bromide is an extremely weak conjugate base. It's a good leaving group as well. A little bit less weak of a base than iodide. It's a little bit less good of a leaving group. But for the most part, they're both really good leaving groups. Take one more example. I think we use this in our talks. Chloromethane. Chloride is the leaving group. Hydrogen chloride is the conjugate acid. pKa is about -7. Depending on the textbook, you'll see -6 or -7. Again, chloride is a very weak base. Hydrogen chloride is a very strong acid. It makes sense that chloride should be a good leaving group. I'm going to show you one more example. We'll come back to this in just a moment. This one's a little hard to wrap your head around, so we'll see the applicability in a moment. All right, what I've written here is protonated tert-butanol. In other words, it's a tert-butyl group connected to OH2+. That's not a compound that you could put into a bottle. It's an intermediate. And so I guess I'll show it in brackets just to remind us that this isn't a compound that you could go to the Chem stock room for your Chem 51 lab course and say, give me a bottle of it. You could get them to give you a bottle of iodoethane or a bottle of bromotriphenylmethane or a gas cylinder, because chloromethane is a gas cylinder of chloromethane. But you couldn't get them to give you a bottle of this, forms as an intermediate in various SN1 reactions. But let's take a look for a moment. What's the leaving group when this leaves? Well, if you're going to take away Cl and get Cl minus, if you're going to take away Br and get Br minus, if you're going to take away I and get I minus, then you're going to take OH2 plus away when it leaves with its pair of electrons and get H2O. Is H2O a good leaving group? We apply the same thought processes. The conjugate acid of H2O is H3O plus. H3O plus has a pKa of negative 1.7. It's the strongest acid which can exist in water. It's a strong acid. In other words, surprise, surprise, OH2 plus is a good leaving group. So those are some good electrophiles. Let's look at some bad electrophiles. For comparison, because you're going to be seeing more potential electrophiles as you progress through the 51B series, and it's important to be able to figure out what's actually going to be an electrophile in a reaction and what's not. And I'll put this in quotes, since if they're bad electrophiles and don't react as electrophiles, they're not really acting as electrophiles. But let's make our comparison here. So these are compounds that don't participate in nucleophilic substitution. I'll just pull some examples out of a hat for the sake of comparison. I'll put electrophiles, we'll make up the same sort of little table. I'll put electrophile in quotation marks, since as you're going to see these molecules don't react. So let's look at ethanol, CH3, CH2, OH. If ethanol did participate in a nucleophilic substitution reaction, our leaving group, and again I'll put it in quotes because it's not going to leave, our leaving group would be OH minus the conjugate acid for OH minus is H2O, water. Remember how I talked talked about, when I talked about water, I said, remember, it's confusing. Water is amphoteric. It can act as an acid or a base. We want to make sure to keep track of whether we're talking about H3O plus, H2O, or OH minus. Well, here we have that situation. We're thinking our way through slowly. Here we have OH minus as our putative leaving group. The conjugate acid of OH minus is H2O. The pKa of water is 15.7. In other words, water is not nearly as weak, not nearly as strong an acid as these acids here. Water is a much weaker acid than H3O plus or HI or HCl. In other words, OH minus is much less happy to exist than, say, I minus. It's a lousy leaving group. Ethanol doesn't participate in an SN2 displacement reaction in which OH minus leaves. Take another example, again borrowing from some familiar pKa's. Methylamine, CH3NH2. If methylamine were to participate in an SN2 displacement reaction, our leaving group would have to be NH2 minus. NH2 minus has a conjugate acid of ammonia, NH3. NH3 has a pKa of about 38, 35 to 38, depending upon the textbook you consult. In other words, ammonia isn't much of an acid at all. It's a very, very, very weak acid. NH2 minus is a lousy leaving group. And you think about this, and this is actually important for making sense of reactivity. Because I've just shown you reactions in which nucleophiles react with things like methyl iodide. And we'll happily write a reaction of Cn minus plus CH3I goes to CH3Cn plus I minus, an SN2 displacement reaction in which iodide leaves. And you're happy to say, oh, that makes sense. So now I write an equation on the blackboard with CH3NH2 and Cn minus, and say, well, doesn't it make sense to write a similar displacement reaction? Iodide's electronegative, nitrogen's electronegative. You might think that Cn minus would want to react and do a nucleophilic displacement and kick out NH2 minus and form CH3Cn. And what's the big difference? The big difference is that iodide is a great leaving group. It's happy to have that negative charge. If you offer it a proton, it's not eager to take that proton. NH2 minus is a lousy leaving group. It's a strong base. If you offer it a proton, it rapidly grabs it up. It doesn't want to give up that proton, and it doesn't want to give up its bond to the methyl group. So cyanide doesn't react with methylamine, but cyanide does react with methyl iodide. All right, one more example, and this will show us a gray area in all of this. All right, let me extend my table down to this blackboard, just because things are getting a little bit crowded here. This is a good one to wrap our heads around. Methyl acetate. Just like we've been considering a methylamine, we'll consider acetate as our putative leaving group. CH3 COO minus. Conjugate acid of acetate is acetic acid, CH3COOH. pKa of acetic acid is 4.76. So acetate's not nearly as strong a base as hydroxide. It's not nearly as strong a base as amide anion, as NH2 minus, but it's a much stronger base than chloride or bromide or iodide. And so for something like that, we would generally say not much of a leaving group. And this, for me, really defines the cusp. Because I can give you examples of SN2 displacement reactions where a nucleophile comes and attacks a methyl group with an ester attached to it, like methyl acetate. But they're pretty rare and pretty specialized, and that's really right about the edge. And remember how we had this table of acid strength, and I said, well, there are really strong acids, and then there are weaker acids, and then there are very weak acids, and I think I put them in quotation marks. It's right in that middle category where you get the cutoff. The very strong acids have conjugate bases that are great leaving groups, HI, HBr, HCl, sulfuric acid, etc. The weak acids, like acetic acid, are just on the cusp. So I wouldn't say, for example, for chloride as a leaving group, never, but it's in a very different category. Remember, HF has a pK of 3.2. It's in a very different category from the other halogens. And I'd say 5 is right about the cutoff number for where you go from something being a pKa of a leaving group to something being a pKa of not a leaving group. All right, so to drive home the point of what I was saying, if I took, say, ethanol plus cyanide, you would be very safe in saying no reaction, or at least no reaction that you've learned of as of yet. In fact, they don't react with each other, but I'll say more specifically, no SN2 and no SN1, no nucleophilic substitution. Now, if I take something like tert-butanol, with aqueous HCl, so I'll write HCl in water, your first thought might be to say, oh, well, that's not going to react. You just told me that OH minus isn't a leaving group. But we've got acid here. HCl dissociates to form H3O+. It's a source of protons. In other words, in aqueous solution, we have an equilibrium where protons go on and protons go off every Lewis basic atom in the molecule. And so we have an equilibrium where we protonate our tert-butanol. And now you say, wait a second, that's a game changer. Water can leave. Water is a good leaving group. pKa of the conjugate acid, H3O+, is -1.7. In other words, we can form a tertiary butyl carbocation. And we have chloride present. Chloride's a nucleophile. Right? HCl and H2O dissociates to H3O+ and Cl-, and there's plenty of chloride around. Plus chloride gives rise to terbutyl chloride. And in fact, this reaction occurs. If I dissolve terbutanol in aqueous HCl, I get terbutyl chloride. Now I showed you the exact reverse reaction, well, except for bromide. I showed us that when we dissolve terbutyl bromide in water, we got terbutanol. What's going on? Do we get the halide or do we lose the halide? Any idea how to make sense of that? This reaction's in equilibrium. Every step is reversible. If you have a lot of halide, you drive the equilibrium to the right. If you don't have a lot of halide and just have a lot of water, you drive the equilibrium to the left. All right, I want to talk now a little bit about various properties of nucleophiles. Finish up our discussion by talking about the nucleophiles. Well, SN2 reactions are hard because they require a nucleophile to get in and to give a push to the leaving group. You need to form that trigonal bipyramidal transition state. As a result, you need to have a good nucleophile. Weaker nucleophiles are not good at SN2 displacement reactions. If I take bromopropane and I mix it with ethanol, ethanol is a fine electrophile, a fine nucleophile if you've got a really strong electrophile like a carbocation that just wants an electron pair from anyone or anything. But on the other hand, for the most part, you'll have very little reaction if it's got to get in and push out a leaving group through an SN2 displacement reaction. Now, imagine for a moment that we first take away a proton. In other words, instead of having ethanol, we have ethoxide, CH3CH2O-. And again, we have propyl bromide. Now we have a very different situation. Just as ethoxide is a stronger base than ethanol, a much stronger base, and wants to share its pair of electrons with a proton, it's a stronger nucleophile than ethanol and wants to share its pair of electrons with a carbon. So ethoxide plus propyl bromide readily undergoes SN2 displacement reaction. You'll learn more about this reaction next quarter. It's called a Williamson ether synthesis reaction. The other product of reaction, of course, is bromide. And so a general principle is if we're comparing atoms of the same type, in other words, an oxygen or an oxygen, for atoms of the same type, a stronger base is a stronger nucleophile. an oxygen and an amide. Oxygen and nitrogen would be a tougher comparison. You can get away with it. There end up being subtle factors. And the biggest subtle factor is solvent here. When you don't have issues of solvation, then the general rule is a stronger base is a stronger nucleophile regardless of atom type. But very often the stronger base is often more solvated, particularly when you have a protic solvent like an alcohol, something with an OH group. Then the stronger base ends up also being more solvated and less available. There's another class of solvents called dipolar aprotic solvents. Your textbook talks about them: dimethyl formamide, dimethyl sulfoxide, acetone. These solvents are very good at solvating the cation, but not good at solvating the anion, the nucleophile. In those solvents, you get a direct correlation. Stronger base is a stronger nucleophile regardless. But very often in protic solvents, a more large spread out charge, like a sulfur versus an oxygen, ends up being a better nucleophile. So even though ethane thiolate, CH3, CH2S minus, is less basic than ethoxide, pKa about 10 for a thiol, pKa about 17 for ethanol. Even though that's the case, in many solvents, ethane thiolate would be a better nucleophile. So this generalization here really works regardless of solvent, but it's otherwise a little bit more complicated because of solvent. All right, what are the last couple of points that I want to make? I guess one point is, in general, not surprisingly, in this trend we see, in general, iodides are better than bromides, are better than chlorides in SN2 displacement reactions. I'll write this as Ri better than RBr, better than RCl, and we've already talked about fluorides in SN2. Say better electrophiles. And the implication of this is that if Johnny or Buck is trying in the laboratory to carry out an SN2 displacement reaction and grabs a bottle of the alkyl bromide and tries to get the reaction to go and mixes the chemicals and monitors by thin layer chromatography and heats it, and the reaction is very slow and it doesn't go, the next thing that Johnny or Buck might do is to go back to the shelf and grab the alkyl iodide with the assumption that since iodide is a better leaving group, since HI is a stronger acid than HBr, that the reaction will go a little bit more rapidly. So that's another good trick. I'll just very briefly write out a couple of thoughts on solvents. So the first thing, of course, becomes, why do we need solvents in general? Well, polar solvents are generally needed for SN2 displacement reactions and SN1 reactions. Well, let's say SN2 particularly. To dissolve ionic compounds. Remember we talked about like dissolves like? And there are two main classes of polar solvents. There are polar solvents with protons, like alcohols. And there are polar solvents without protons. By protons, I mean that you have a proton on an electronegative atom that can hydrogen bond. So things like dimethyl sulfoxide, acetone, dimethyl formamide. All of these are good solvents for SN2 displacement reactions. All of these solvate nucleophiles. As I was mentioning before, nucleophiles in these solvents are relatively unsolvated. I should say they all are good at solvating ionic compounds. In the case of a polar protic solvent, a nucleophile Nu- ends up being hydrogen bonded to and being tied up. And so this is the particular case where bigger atoms end up being better. Whereas in these solvents, you're very good. All of them have a nice delta minus on the oxygen. They're all very good at solvating the cation, not so good at solvating the anion, so you have a naked nucleophile that's available to react. Well, this is a good point to wrap up. Have a great Thanksgiving. I will see you again on Monday, and we will discuss in our last 3 lectures, Chapter 8, Elimination Reactions.